Good afternoon, guys. Hopefully, when you watched that video last night, a lot of this should be a simplistic review. Here's the reason why I wanted you to watch that is because I wanted to make sure that something that I said connected to what she said. Because sometimes the way Renee McCormick explained things, she does a really good job, but it's kind of abstract. And I've watched all of her videos, so I know how she teaches, I know how she prepares. And so there are some things that she goes from A to C really fast, and she'll leave out B. And so that's when I feel like I need to go in and just change some things. Now, this was a diagram that kind of looked like what she was showing you all last night. It may be the exact one. Is it the exact one? Yeah. All right. Here's the purpose of this thing. This mass spectrometer or mass spectroscopy or there's a few other things the way you could say it. The whole purpose of this device, if you will, and guys, this is a very, 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 very simple drawing. I was actually going to show you guys a video of a real one, but you would have been asleep in about 2.5 minutes. So I'm not going to bore you with those details, but I still want you to understand what the purpose of this is for. It's so you can determine the number of isotopes of a particular sample of element. Okay. So the way she explained it is in the sample. Let's just pretend that in this sample that it's going to be nitrogen, just to make sure it's the same sample. So again, hopefully she explained the way it worked is when you put that sample in, you send it through a charged flow of electrons. Now let's talk about this for just a second. Why in the world would you have to put electrons on something to make it be charged? Okay, but we're adding electrons to it. We're bombarding with electrons to make it charge. To create a flow. It's basically going to create this flow. So here's what's going to happen. It's passing an ion accelerating electric field. So what do you think that thing's making it do right there in these slits? Accelerating.
It's just like a catalyst.
It's speeding that sucker up, right? It's making it go a lot faster. Now, magnetic field. This is the key to all of this. What is that magnetic field doing to that charged particle? It's separating the masses. It's deflecting them. So let's talk for just a second. If you've got something that has one electron, but its isotope is really, really, really light, okay? Matter of fact, let's go this way. Let's go into football terms, okay? If I was going to run head-on into Alex, and then I was going to run head-on into Andrew, which person would deflect more once we hit? Why Alex? Because he's smaller. So when you send a lighter mass particle through a magnetic field, which one will the magnetic field affect more? The lighter mass or the heavier mass? The lighter mass, all right? Well, let's talk about something real quick. What if you send a really light particle through here, and it's so light that it slams it into the glass here? Will it ever make it to the detector? Nope. What if it's so heavy that it won't even make it, and it just slams into this? Or it's so heavy that it doesn't make the bend, and it slams in. Could that affect your results? Yeah. If it affects your results, then we're not looking for it. We're looking for something that is nitrogen, okay, and we can figure out based on the strength of the magnetic field of how it works. Here's the most important thing that I want you to highlight on this is the top is going to be your least massive ions and the bottom are going to be your most massive. And again, why are the most massive ions on the bottom and the least are on the top? It's the effect of the magnetic field. The lighter the particle, the more affected it becomes. The heavier the particle, the less effective it becomes. Now, I told you this was a very basic diagram. The ones that they actually use, they're a little different than that. They actually have 3 beams. So let's just pretend that this is the sample. It's going to come out and it's going to bend like this, and then it's going to go like this, and then it's going to take another bend. And there are actually 3 magnetic fields in the real one. There's a magnetic field here, there's a really big magnetic field here, and there's another one right here. And every single time it flows, it accelerates it faster and faster and faster. And then you have the receptor plate down here. So there are 3 locations in the real life one. Ignore the picture behind it. I'm just drawing a different version, okay? Yeah, ignore that picture behind it. Matter of fact, let's just do it like this. Okay? You've got the sample here, and you've got the tube that comes out. You've got the receptor plate here, and you have the magnetic field here, here, and here. Okay? So there are 2 places that it could actually, if it's traveling, it could hit up here, or it could dive here. It could hit this outer wall, or it could hit this inner wall. So it's basically making it be perfect to be able to get to the final. So like if it was a particle, it's got to be perfect to be able to make it through. Okay, somebody have a question? Yes, sir. Let me go back to this. If you'll notice, there's a heating device to vaporize the sample. So basically, if I put in something that's like carbon pellets or charcoal, charcoal is nothing but carbon, right? When it heats it up, it's going to get so hot, it's going to turn it into a gas, and it basically shoots that gas down the tube. So essentially, you heat them up, speed them up, is exactly what we're doing. So that's what that coil right there is doing. It's making it so hot that it's air as well, and the air is forcing it that way. Okay? Oh, these things are huge. I mean, they take up probably the size of my office. Oh, they're really big machines.
I'm saying like this is only like a part of it.
A part of one, yeah. They basically scaled it down. Yeah. So imagine that like this continuing, like it would continue and then it would bend again, and the receptor plate would be way back there. Does that make more sense? Okay. Alrighty. So let's move on to the next part. So what's the purpose in actually doing this? Well, one of the things we talk about, the actual mass of an atom was not known until the invention of this thing. So that's how important it is. So we would not have this unless we had the spectrophotometer. So that's why it's an important topic to teach. In mass spectrometer, ions of high mass, and this is the key that I want you to highlight, okay? Ions, let's try that again. Ions of high mass deflect less than those of low mass. That's really important. And again, why is that true? Okay. Yes, they're heavier, but what's affecting it? They're not as affected by the magnetic field. Okay, that's the key there. All right. The third bullet, if the charge on the particle is known, then the mass of the particle can be calculated. Read that one more time. If the charge on the particle is known, then the mass of the particle can be calculated. Let's talk about this for just a second. The mass of the particle. What will give you the mass of a particle? Very good. The protons plus the neutrons. So here's the deal. How in the world will the charge give you? Because what's making it charge? What are we adding to it? Electrons. But wait a minute. You just told me that the mass is coming from the protons and neutrons, not the electrons. So what does that have anything to do with it? And it all boils down back to this. If they're all charged equally, are they going to deflect into different areas? Well, once they deflect in different areas, it's going to tell you what their mass is. Okay, does that make sense? Based on its deflection points. The lighter the particle deflects more, right? The heavier particle deflects less. And so you can come up, and the computer will tell you what it is. Okay? No, it'll be exact because it'll come up on the screen what its exact mass is. That detector plate has the ability to detect its mass. Okay? All right. All right, here's something that you pretty much already know. Atomic mass units, exactly proportional to 1/12 the mass of a carbon atom. You don't really need to know that. Isotopes, atoms of elements having different atomic masses because of what? Okay. If you're not quite sure about that, because of number of neutrons. That's why. Okay, that's why we have isotopes. All right, the bottom part, the average. Okay, we don't really need to know that. And then looking at this. All right, so here's the deal. Do you all agree that there is carbon 12, carbon 13, and carbon 14? These are all different what? These are all different isotopes. Now, let's read the statement at the top for a second. The atomic mass is the average. The atomic mass is the average of all of the naturally occurring isotopes. It's the atomic mass is the average of the isotopes. Now let me stop for just 1 second. Do you agree that these numbers, 12, 13, and 14, are the masses of those isotopes? If I take the average of 12 plus 13 plus 14 divided by 3, what's the average of that? 13. However, here's the important part. When you look up the mass of carbon on the periodic table, what is it? Thank you. So, since the mass of carbon is actually 12.01, is it the true average? No. What other factor must be applied here? Say it again. Percent abundance. Very good. So over here, please write that. Please write percent abundance. Is it fair to give carbon 14 just as much credit for the mass as carbon 12, even though carbon 12 is 98.89% of the atoms out there? So what I would be saying is, here's a bag of 100 carbon atoms. The average mass of the atom in that bag is 13. However, 98 of those things are carbon 12. Is that fair? No, not at all fair. But that's exactly what we're saying here, is that of 100 carbon atoms in that bag, 98 of them, almost 99 of them, are which one? Carbon 12. So to account for the average mass, you must also account for how relevant they are, or how abundant they are, or how prevalent they are. So this is something that you're going to have to learn how to do. She did one of these problems in the video, but guys, I'm telling you now, you're going to see it all over the place. You're going to have to know how to work on it, okay? This is an actual diagram of a mass spec reading. Some of the things you're going to have to learn how to do is read your graphs. You have to look at the X and Y axis. What is the y-axis telling me? Percent abundance. What does percent abundance mean in basic terms? Yeah, if I walk outside and start digging it up, how often will I find it out of 100 of them? Okay. Mass, we get. What specific element are we working with right now? Copper. Very good. Now, how many isotopes of copper are there? How do you know there's only 2 isotopes? There's only 2 peaks. That's it. What are the 2 specific copper isotopes? Cu what? 63 and Cu what? 65. Very good. Does everybody see that now? All right. So, what is the average of 63 and 65? 64. However, here's your test. What is the actual mass of copper on the periodic table? Does anybody know? Very good. 63.55. All right. Did you? That's fine. All right. So the actual mass of copper is 63.55. But the average is 64. So where did they come up with this number from? What did they also account for? They also accounted for your percent abundance, right? Which one, if you went out in the nature, would you find more often? 63. Very good. So this one is more abundant. Okay. Specifically, how much is abundant ant or int? Thank you. Specifically, how much more abundant? What percentage is 63? I'd say that's what, about 69? All right, what is 65? I'd say that's what, about 31? So what's the difference? 38? So you're looking at 38%, right? So if you went outside and started digging for copper, 38% more often you'd find copper 63. Do you agree? So we need to give more credit to copper 63 because it's found more often. So let's look and see how we would do that exactly. This is the part that's going to be on the AP exam. You're going to have to do this, okay? So how would we figure this out mathematically? Here's the shot. So we have copper 63 at its mass, and we have its abundance, 69.09%. We have copper 65 with its mass, and it's 31.91%. Okay? So, do you agree that this number right here is the number on the periodic table? Well, here's where they got it from. Mathematically, what did they do right here? Multiply what? It's the mass, what? Mass times percent abundance. And then what did they do to both of those numbers? They added them together. Now, to me, they did a lot more work than they should have. Do you agree? Could you not turn that into one linear problem? Me personally, what I would have done is I would have put a plus sign right here, and I would have written this part right there. And couldn't you put that whole thing in your calculator and just hit equals and there's your final answer? Okay, that's what I would recommend doing. I'm telling you now, you're going to have to be able to do this on the AP exam. Write that down. Mass times percent abundance plus how many ever isotopes you have. If it's 12 isotopes, you got to do it to all of them. We're going to practice that in just a second. Again, it's mass times percent abundance. Now, here's the only other thing that I want to show you. These percent abundance numbers are not the same as they are down there in the math. Why? Why did you not plug in 69.09? Very good. Percents, are they real numbers? No, they're just easier way to look at them. So what did they do to get the actual mass or the actual number? Just move the decimal where? 2 places to the left. I'm forewarning you, this is the most messed up part of the people's problems. People forget to change their percents to decimals. They leave them as big numbers, and they come up with these crazy huge numbers. Because here's how they're going to ask it on the exam. They're going to say element X has this percent abundance for each isotope. What is element X? So can you look on here and tell what its mass is? You can't cheat. You're going to have to figure it out based on the math. You're not going to have any clue what element it is. So you can't just look on here. You're going to have to be able to do the math part of it. Okay? All right. The only thing I want to show you about this is we know that the atomic mass of an element is made up of what two things? Okay, protons and neutrons. Have you ever been curious why the electrons don't make up the mass? Because they are also present. Why don't they? Notice this. Is the electron much lighter than both protons and neutrons? Now, you're thinking, well, it's just 4 decimal places. But think about this. It's already at 24. There are 23 zeros this way. Well, if you add 4 more, didn't it just get a lot smaller? It got way much smaller. So really, the relative mass, the electron is 1,837th, that th of a proton or neutron. It's that much smaller. That's why we never actually calculate electrons into mass. Okay? Even when they're charged. When you add 3 electrons to nitrogen, does it change its mass? No, not at all. You're not adding that much mass to it. Okay. The atomic scale, this is pretty interesting. So you have the protons and neutrons, protons. We have this thing that makes up protons. What are they called? Yeah, they're called quarks. But notice this. What is the relative size of quarks and electrons? Look at this. Notice this. Quarks make up protons. Do you agree? But look what happens. We go from the nucleus to this thing, and then a proton, and then a quark makes up a proton. But look how real tiny the electron is. Okay, they are equivalent. That's how small an electron is. So you could essentially say an electron makes up protons. They're so tiny. That's kind of what that's. Yes, sir. To be quite honest with you, I've never really studied quarks. I don't. Yes, sir. Tell us. Let's hear it.
There's I think 6 types of sports. There's up, down, strange, charm, up top and bottom sports.
Have you been reading?
I like particle physics.
Okay.
And they all have different weights. And the up, the top, and the charm all have positive 2/3 charge.
Okay. Just. I follow you, but you are doing. All right. Here, quarks. Okay, you're with me. Quarks make up protons, right? Bones make up your skeleton. Quarks make up protons. There are 6 different types of quarks. 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 And apparently he's done a lot more research than I have because I had no idea about any of that. There are 6 types of quarks: up, down, left, right, top, bottom, something like that. Up, down, top, bottom, charm, and strange. Okay? And apparently they all have different masses. Something about 2/3, something like that.
Protons made up 2 up quarks and a down quark, and neutrons made up 2 down quarks.
All right, let's just quit there. All right, that's ridiculous.
That's it right there. Look, these 2 up quarks and a down quark, 2 down quarks.
Now, can we skip this slide?
Wow, he literally just got it right. On the list. It's on the list.
I'm pretty freaking impressed, dude. That's nice. All right, so what he was saying, if you're watching this video, is that this thing right here is a neutron. No. The 2 that are circled right now are protons. Okay. The reason why is because he said it's 2 up quarks and 1 down quark, and then the 2 neutrons, which are circled now, the green circles, are made up of 2 down quarks and 1 up quark. Dude, I'm impressed. That's well done.
Because the down quarks, down quark only has 1/3 negative charge.
Okay, I'm with you, which makes it neutral.
Yes.
Okay.
You have 1 up because it's 2/3.
Okay, so they cancel each other out.
But if you have 2 up,
That's more than.
1/3 more. So it's 1/3 positive.
Wow. It makes so much more sense now. So basically what he just answered is why are protons positive and why are neutrons neutral? The quarks cancel their charges out. So in a neutron, there's the same number of pluses and minuses. But in the proton, there are more pluses than minuses. And yeah,
Oh, that makes sense.
that's exactly what he just said. Okay?
Why didn't you just say it like that?
Because he's talking in particle physics. So that what he just answered is why are protons positive and why are neutrons neutral? Things make up those 2 things, and they balance each other out. Now, here's the fun one. Quarks are held together by gluons, so it gets even smaller. That's an interquark force, an IQF. Or called a strong force. That was a joke that you just made not funny anymore. Because you took it way too serious. I'm serious, Jacob. That's impressive. That's well done. I've never heard any of that before. Well done. But it's protons are made up of 2 up quarks and 1 down. So there you go. Well done. All right. So that's we're done with that slide. Now open up the mass spec worksheet, please. Yeah, you've just been demoted, Alex. You are no longer the smartest.
That's all right. I handed my title to Jacob Irvin.
That was well deserved.
Yeah.
Give me just one second.
Don't worry, I lost my iPad, so I'm not
Here.
very bright.
Are you like this in every class?
Well, I know my stuff classes, but I know part of it. I haven't taken it yet.
Why have you not taken it? You're a senior.
I'm a junior.
Oh, my bad.
Richard,
Yes, ma'am.
do you have Logan Ledbetter?
I do.
Please send him for checkout.
Okay.
Thank you.
Do you know about Logan or Chase? That's what I thought, but they called you Logan today.
They called everybody by their first name.
Chase looks up every day.
Let's look at this. All right. Now, I'm going to be honest with you. Once we're done with this, mass specs should be very simple to you. Here's the most important thing. You're going to see this on your test. Like, test is going to be Thursday. Test is Thursday. You're going to see this on your test. So I would pay attention to this. Now, I want to pretend for just a second that they give you none of this information at the top. Just look at the picture for just a second. Remember, whenever we look at graphs, we look for the axes to tell us a lot. Whenever you see relative abundance and you see mass, you're looking at mass spec data. Yes, sir. It's not per se. Because here's how it's related to stoichiometry. Do you need molar masses for stoichiometry? Yes. This is the only way. It's because it's teaching you how to find technically the molar mass. Okay? It's the actual real way of finding molar masses. Instead of using the periodic table. Yep. It's, again, they're going to ask you the questions. When you see these questions, I promise you it'll make sense later. Yes, sir. Oh, absolutely. Yeah, but it's going to say element X. You're not going to have any clue what element it is. Okay? Yep. All right, so here's the deal. Knowing where the most abundant mass is present, if you do have a periodic table, you can kind of narrow it in. Looking at this, which mass is most abundant based on the picture? 35. Which element is closest to 35?
Chlorine.
What?
Chlorine.
Chlorine. Chlorine is 35.45. So, but if you actually had this piece of data up here at the top, it tells you peak 1 is due to what?
Chlorine.
Chlorine, which specific isotope?
35.
So do me a favor. Label this tallest peak Cl35. All right. So that's telling me that that tall peak is the chlorine atom with the mass of 35. All right. Well, now let's move to the next one. What do you think this second peak is? It's chlorine what?
37.
37. All right. Well, let's talk about how that happened. How did it change from chlorine 35 to chlorine 37? It added what? 2. Now let's talk about why. We know it's 2 because there's a difference of 2. Why did it not add 2 protons? If you change protons, it changes the element. What's element? 20 is calcium. So we have to stay within it. We know isotopes are different masses because they have different neutrons. So here's Jacob and Chase, y'all be quiet. Now, where in the world and why did all of a sudden those 3 extra way down the line dots just all of a sudden, those peaks just show up? This was all red at one time. So if I send one shot through, one shot got 35, one shot got 37, then 70, then 70 something, then 74. Where did that come from?
They react differently to the magnetic field.
Jacob? Chase?
Did they bond together?
Okay, go a little bit deeper when they bonded together.
CO2.
Very good. These are your diatomics.
What?
Very good. We know that chlorine is never by itself. What is it always like? What's 35 plus 35? Where's that next highest peak? At 70. So, if you ever do a gas that can act as a diatomic, it's also going to show up. So let's pretend for just a second. Let's completely change this graph and let's change it to nitrogen for just a second. Where will the highest peak, what mass would the highest peak of nitrogen show up? 14. Where would another really high peak be? Why 28? Nitrogen's a diatomic, so its next highest peak would be where? At 28. Let's flip this to oxygen. Where would the highest peak of oxygen be? 16. Where's the next highest peak? 32. You starting to see what happens there. All right. Now, that explains, you're basically, what I'm taking is this element 3 is a Cl35, and it's stuck to another Cl35. Because what's 35 plus 35? 70. Hang on one second, Chase. So now we have another one to deal with. Now we've got 72. How did I get a 72 to show up? What had to happen? 37 and a 35. So peak 4 is going to be a Cl35 plus a Cl37, which is equal to what? 35 plus 37 is equal to 70 what? 72. The last one, what's this little bitty baby peak number 5? That has a mass of 74. What was that stuck together? 37 and 37. So does that make sense?
A little bit.
So what has happened is we have the ability to have, in this quadrant, we have the elements, one atom right by itself. Do you agree? And how many elements or how many isotopes are there? 2 different isotopes. But then, if it has the ability to become a diatomic, you can all of a sudden have these. So, if you've got 2 isotopes, you can have 3 different variations of the diatomic. Now let me flip the script on you one more time. Now, let's look at carbon. We know that we have carbon what? Carbon, that's completely wrong. What am I doing? Carbon 12, carbon 13, and carbon what? Where will the highest peak be? 12. Do y'all agree? All right. Where, let's pretend that carbon can make a diatomic. Where would another high peak be for a carbon diatomic? Very good. So do you agree to get the 24 peak, you would get C12 and C12 combined? How many other peaks could you have with that kind of a combination? Say it again. Very good. How did you come up with 6 total? All right. So C12 can also be with what? C13, and it can be with what? C14. What would the mass of 12 and 13 be equal to? 25. What would the mass of that one be? 26. Now, can 13 be with something else? What can 13 be with? C13 can be with C13, right? Have I used that one yet? Okay. What else can C13 be with we haven't used yet? C14. All right. What's the mass of C1313? 26. Something weird has just happened. You've got 2 masses of 26. So will those peaks be different or will they be the same? So could you tell which one was which? Nope. And then what's the mass of 1314? 27. Is that an okay peak to have? Yep. And then finally there's one more. 1414. And what's its mass going to be? 28. So let me start over. we're going to have total 9 peaks on this graph. Do you agree? The elements by themselves would be those 3. Do you agree? You'd have the highest one at 12, and then another one at 13, and another one at 14. And then if it could form diatomics, it would form all of these. Technically, it would really only be 8. Why 8? Because what are those 2 going to do? They're going to stack together.
What about like sulfur? It has like 8.
Well, I don't know how many isotopes sulfur has. That's true.
It'll be the same thing.
That's a good point. So S8, it would be way off the graph. That's a great example. S8, remember that we could have that? It would be so heavy, it would slam into the glass before it ever made the count. Does that make sense? You know, we have carbon-60 too. There's a low probability of it forming in that tube, but if it did, it would never make it to the reader. Okay?
So, you said another high peak would be 24.
Yeah, because it will be 12, 12 stuck together.
So why would it be 14 and 14 because 12 is more abundant?
Yes, because 12 is more abundant. Remember, the 14, carbon-14 was like 0.01%. The chance of having a 14-14 is like going out there and digging up a dinosaur bone up there in that yard.
So you just knew that 12 was more abundant.
Because we saw that earlier. It was 98.89%.
So you're going off.
Yep. All right, so let's answer these questions tomorrow or Monday. Y'all have a good weekend, guys.